Hello guys, and welcome to my video. Today we're going to be focusing on a very special paper, the October-November 2023 question paper 2.2 for physics. And this is a very special paper because it was written recently last year in the October-November series, and it's going to be a very good paper to help you practice if you're hoping to write AS this year or you are hoping to write AS in any year. This is going to be a good practice paper for you. One tip that I have is try at least to work some of these questions out before looking at the marking scheme or before looking at how I'm going to be able to work this out, so you can get to think and get to engage your mind in a lot of things. And again, if you find this video useful as well as other of my materials, please do subscribe, like, and comment if there is anything unclear or anything that you liked about my video. So let's get to it. So the first question is a question on SI base units. So the question reads as follows. We have been given a list and we've been asked to underline all quantities that are SI base units. So this question requires you to know two things. The first thing is you need to know what base means. You also need to know what a quantity means in the context of physics. So those are very two key distinctions that you need to make. What is a base unit, or a base quantity rather, and what is a quantity itself, right? So a quantity is something that you can measure, a measurable aspect of matter or anything at all that has magnitude and units. So if you can measure something and it has magnitude and units, it is a physical quantity in physics. But not all quantities are base quantities, because the word base comes from something which is basic, which lays the foundation for everything else, meaning that base quantities are quantities that you can't make out of anything else. They're quantities that have been set, and they're quantities that define everything that we have. We've got a lot of these quantities, right? They can be time, they can be length, they can be temperature, they can be current, okay, they can be mass. Right, what else do we have? We have a lot of these quantities. It can be amount of substance. If you do A2, it can be light intensity. There are a lot of different base quantities. Their base temperature cannot be split into anything simpler. So in this case, if we're going to underline two quantities, it's going to be electric current and it's going to be time. So we've just been asked to underline, so we underline electric current and we underline time. Charge is not a base quantity and force is not a base quantity. Move on to another equation. We'll be given under certain conditions, the distance s moved by the object in a straight line in time t is given by that following equation. S is equal to half at squared, where a is the acceleration of the object, and we've been asked to state two conditions under which the above expression applies to the motion of this object. Let's conceptualize this. Let's assume that this is a car, right? You have a car, which is our object in this case, that's moving in a straight line. So it's going to move from point A and it's going to arrive to point B. So the car is moving in a straight line, right? And we've been told that the distance s that has been moved by that car, so you have a very nice car, it's going to move a certain distance. The distance s that has been moved by that car is going to be equivalent to half its acceleration. So whenever a car starts, it's going to have a certain acceleration and it's going to have a certain time frame that is going to cover that distance. So s will be equivalent to half at squared. Now the question has asked me, state two conditions under which the above expression can be true. Well, what else do I know? I've seen this expression before. I feel like I've seen it. Well, if you've done Newton's laws of motion, you're probably familiar with this equation. S is equivalent to ut plus half at squared. What's the difference between this equation and that equation? The major difference is that there is no ut expression, but we know time is there, right? So the only logical explanation is that u has to be equal to 0 for that expression to disappear. So an assumption that we're going to make is that the initial velocity, okay, so the initial speed or velocity of that object, so the initial speed or velocity, right, so the initial speed or velocity, okay, is going to be 0 for that particular object itself. Another assumption that we can make is that the acceleration is going to remain constant, because if acceleration changes, you can no longer say s is equal to half at squared, right? Because the a keeps on changing and changing and changing, meaning that this relationship will not hold true. So this relationship is only true if acceleration remains constant. Okay, so if acceleration remains constant or slash is uniform. So if acceleration is uniform or it remains constant, it's going to agree and abide by the equation of motion. Okay, The next question, the variation with time t of the velocity v of a car that is moving in a straight line. We have our car again, right? A very, very fancy car. So, the car is coming back now and again. So try to conceptualize physics questions. Imagine you're the owner of this car, right? So try to think of what does this graph mean? We're going to get it in a few minutes. We're just going to answer some of these questions and we're going to come and interpret what this graph actually means. So we've been asked to compare the acceleration of the car at time t is equals to 8.0 and time t is equals to 14.0. What do we know? We know that the acceleration of an object, right? The acceleration is going to be the gradient, right, of a velocity time graph. Okay, what does this mean? If a velocity time graph, the acceleration is going to be the gradient of that graph. Okay, so it means that the gradient of this graph is going to be your acceleration. So time t is goes to at 8.0, right? So it's basically this time, right? So essentially, at this particular point in time, right, you're going to have a certain acceleration that is going to be the gradient of this whole line. So it's basically the gradient of this whole shape, right? But then at time t is equals to 14, at time t is equals to 14, that's basically going to be here, right? At time t is equals to 14, somewhere here. It's basically going to be the gradient again, because it's the same gradient, right? Same graph, same gradient. The gradient of this graph over here, right? So the direction of the gradient, right? This is a positive gradient, right? But then this is a negative gradient, meaning that this negative gradient is opposite in direction to that positive gradient. And as you can see, this graph is more steep, right? As you can see, this graph has to be more steep. So what does it mean? It means that we need to have a greater acceleration, or it implies that it's going to be a greater acceleration because you have a more steep graph. Then this graph is going to be less steep, right? So this is going to be a less steep graph. What does this imply? Less steep means that we're going to have a lesser, okay, a lesser acceleration, right? Just based on those two facts, right? If it's more steep, great acceleration, less steep, lesser acceleration. So in this case, the magnitude, right? So the magnitude, okay, of acceleration at t is equivalent to 8.0 seconds will in turn actually, right, be greater, okay, sorry, it's a t is equals to 14, that's greater, sorry, it's a t is equals to 14, right, that's the one which is greater, so a t is equal to 14.0 seconds will actually be greater than that, okay, at t is going to be equivalent to 8.0 seconds, right? And then again, they're going to be opposite in direction, so the acceleration, okay, the acceleration at t is equal to 8.0 seconds is in the opposite direction, okay? Okay, so time t is equal to 14.0 and t is equal to 8, the acceleration is going to be in opposite direction. And then the question is asked us to determine the magnitude of that acceleration, the acceleration of the car, right? So we want to determine the magnitude of the acceleration. What do we know? We know that the acceleration is going to be v minus u divided by t. So if you go on this graph, get a v that you want, right? We can start here. We can say our v, our final velocity is going to be here, right? And then we can assume that our initial velocity is going to be here. Meaning that we're going to have a certain velocity 20, then another velocity 0. So it's going to be 20, okay, 20 minus 0. Then our time period at 20, we have 12. As you can see, at 20, we have 12. And then at 0, we have 4. So the denominator, we're going to have 12 minus 4. That's going to give you an acceleration of 2.5 meters per second. So acceleration is just going to be 2.5 meters per second squared. It's a very, very important key distinction that you need to be able to make. Move on to the next question. We'll be given a car that is at point x at time t is equivalent to 0. And we've been asked to determine the magnitude of the displacement of the car, x, at time t is equals to 12.0. Now, this is a very, very important question because you're going to have to think and conceptualize a little bit about something that I call positive and negative displacement. And after watching this video, trust me, you're going to understand a little bit much more about what these graphs actually mean and what these graphs actually entail. Okay, so I need you to be thinking about this, right? Let's bring back our car, right? So we have our car, which is going to be, you know, experiencing all this motion, right? So I need you to take note of three things. So you're going to need to know three things: your acceleration, right? So you're going to need to know your acceleration, your displacement, right? So your acceleration, then your displacement x, s, and then your velocity v, right? Those are three things that I want you to know, right? So from negative 10, that is from t is equals to 0, because it x where t is equals to 0, we want to determine the displacement from x to 12.0, right? So we had x is here, right? So I'm going to mark this position and I'm going to call it x. So it's this position and I'm going to call it x. And we want to find the displacement until we move at time t is equivalent to 12. But it's going to be a little bit complicated, but we're going to identify that just in a minute. So for v, the initial velocity, right? So the initial velocity that you have is going to be negative. That's a very important key distinction that you're going to make. The initial velocity is going to be negative, as you can see here, right? But the acceleration is the gradient of the graph. The acceleration is going to be positive. Okay, but the displacement is what we want to find. But what does it mean to say acceleration is positive but velocity is negative? What does that tell me about the motion of this object? Well, negative means it's moving in the opposite direction, right? Negative 10 means you're in the negative direction, right? Your velocity is in the negative direction, right? So let's bring back our car and let's assume we have a road, right? So we're going to assume we have a road like this, okay? Like so. And our car is going to move from point A on this road and it's going to arrive to, a certain point that we want to find, right? So we're going to mark point X on this car, okay? So this is point X, and we have a specific car which is over there, right? This is point X. Let's keep that in mind. Okay, so the car is going to have a negative V. So we're going to say this direction is going to be negative, okay? Then we're going to say this direction is going to be positive. So I want you to keep note of this. So the velocity is negative, but the acceleration is positive. So imagine you're in a car and you're reversing the car. That means the car is moving in the opposite direction. So the car is moving back, right? Reversing a car. So our car is moving backwards. So it's basically moving in that direction, right? And at a time when its velocity is negative 10 and it's moving back, that is where we're starting to measure our time. So when the velocity is negative 10, we start measuring our time. So the car is going to keep on moving back, right? Because it has to decrease until it reaches 0. But how is the velocity decreasing? It's because you have now stepped on the accelerator. The car is now moving back. Then you say, no, I want to step on the accelerator, right? So as you step on the accelerator, the car will try to move forward, right? But the velocity is acting back. So the car would cause that velocity to decrease until it reaches a point where the velocity will be 0. Okay, get this. So we now have a negative displacement from this point up until to that point. We now have a negative displacement that we have done. But as soon as we arrive at this point, that is at this time t is equals to 4, we then start moving forward. Our velocity is now in the forward direction, right? So our velocity is now going to increase from here. Okay, so our velocity is then going to increase from here all the way up to this particular point when t will be equivalent to 12. Very, very important, guys, for you to conceptualize this. So you have a car moving back and it will keep on moving back, right? It's like you saying you're moving forward and you step on the brakes. Your car is not just going to stop and start moving back. It will keep on moving forward until it stops. So if a car moving back and you apply the thrust on the forward, it's going to keep on moving until it reaches 0, then it starts to move forward. So your displacement is going to be this negative displacement plus this bigger positive displacement. So to answer this question, we're going to have a positive displacement that's going to be very big. Then we're going to have from X, we're going to have a negative displacement that's very, very small, right? So if we subtract those two displacements, we're going to get the displacement at t is equal to 2.0. I hope it makes sense, guys. So how can we find the displacement? We know that S is going to be the area, okay, the area underneath the graph, right? So the area underneath the graph, you have a graph, right? So at this point, as you can see, as it arrives at the top, the acceleration again is going to be back, but it's going to keep on moving forward until it reaches 0, right? So it also explains this particular side, right? So try to use that same logic that I gave you. It still moves forward, but now it's accelerating back because the gradient is negative. So just use that fact. Okay, so we're gonna have two triangles. We're gonna have two triangles, guys. We're gonna have this triangle, okay, and we're gonna find the area of that triangle. That's our negative displacement, right? Before it reaches zero, right? This is our negative displacement, right? This is it. So let me just share this. This is this displacement, right? And then at t is equal to 12, we're gonna have this displacement, okay? So this displacement, this is our positive displacement, and it's going to correspond with this entire displacement, right? Like this. So if we add them, positive displacement, negative displacement, we're going to get the area that we need. So in this case, we have half of 12. It's a triangle, 12 minus 4. 12 minus 4 times 20. Then half of 4 minus 0 times 10, right? So basically, just find the area. So we're going to have our area under the graph being 1/2 of 12 minus 4 times 20, okay? Minus 1/2 of 4 times 10, okay? Then we're going to have 80 minus 20 is equivalent to 60. So we're going to have a displacement of 60 meters. Very important, guys, for you to conceptualize these and actually grasp and understand this concept. Again, if you have any questions, anything unclear, please do put in the comment section, right? I'm doing this for you guys. So if you have anything that you don't quite understand, put in the comment section. I don't understand A, B, C, D, and I'll clarify that, okay? Move on to question 2. It's a question on upthrusts, right? We've been given a high altitude balloon that is stationary in still air. Again, this is a hot air balloon, very popular thing. You know, a lot of people ride hot air balloons, pretty fun, right? I've never ridden one before though, but like, okay, so we have this and it's stationary in still air. Very true. Then we'll be given the total weight of the balloon, the string, and the and that guy. Okay, so that total weight is going to be acting down, and that total weight is going to be 65 newtons. 65 newtons. That's going to be the weight acting down. But if it's going to be stationary and the weight is acting down, we need something that acts up. And that thing has to be equal to 65, because if it's greater, it moves up. If it's less, it moves down, right? So, you know, like the hot air balloon is actually like pumped with fire, right? So the fire pumps the whole hot air balloon up, and as that happens, it rises. And then, you know, if it stops, it starts falling down because of the weight and all that stuff. So if you don't put a force, if you don't have a force upwards, then there's going to be a problem. But that force is generated by the upthrust, right? So we're going to have a force up that is due to the upthrust, right? So basically, the upthrust is going to generate, you know, a shape. So the upthrust is going to generate a force that's going to oppose the weight. But we know that the upthrust, right, is going to be equivalent to rho times G times V. This is the expression for upthrust, guys. If you forgot this expression, right, if you go here, you know, you're going to find your expression for upthrust right over here. Okay, so, you know, that's just a very, very important, equation for you to just, know as a student, right? Okay, so upthrust is going to be rho GV. Do we have the density? Wait, that's what we actually want to find. Okay, so our density is going to be equivalent to our upthrust divided by G times our volume. What is our upthrust? Remember, it's equal to the weight, 65, divided by, what is our G? 9.81. What is our volume? 7.5. What upthrust do we get, guys? We get 0.88 kgs m to the power of -3. 0.88. Why did I put two decimal places? Because they're just two significant figures. The smallest significant figures in my answer are 2 from 75 and 2 as well from 65. So your answer should have two significant figures or one more. That's the rule of physics. You have the same significant figures or you add one more significant figure. Very important, guys, for you to conceptualize this. Again, the string breaks. Oh, this is very dangerous, right? So, what if the sphere hits someone? Okay, so this guys. Okay, so the string breaks, right? And then we have like this big sphere that's going to start falling down. Okay, so the string is just, going to break like so. And set the magnitude of the acceleration immediately as the string breaks. So we have a sphere here, right? So our sphere is now going to start falling down. But immediately as it falls down, the only force acting on it, F, is going to be equivalent to mg. That's going to be the only force that is going to be acting on it, right? Where g is going to be 9.81. Immediately as it falls, the weight of that object before air resistance acts is going to be acting down on that object, right? So our mg will be equivalent to our mass times acceleration, because F, right? Because F The resultant force is actually equal to your mass times your acceleration. So from this expression, if the mass cancels out, right, we're going to left with your acceleration is going to be equivalent to g, which is going to be equivalent to 9.81. So you're going to have an acceleration of 9.81. Next question. We've now stated and explained the variation, if any, to the magnitude of the acceleration of the sphere when it is moving downwards before it reaches terminal velocity. So you need to understand what terminal velocity is. So the trick to physics, you have two things that you need to understand here. Magnitude of acceleration, and the other thing is how does it change before you reach terminal velocity. Terminal means it's over. It's a constant velocity, right? So it's a constant velocity where the acceleration is done, the acceleration is 0, and the object just falls with one particular velocity. So it's a very, very important expression that you have to actually explain and actually understand, right? So you have a sphere. Let's go to the basics, guys. You have a sphere that's falling down. So the first thing that's going to happen is your sphere falls down, its speed is going to increase because it's accelerating, guys. If you're riding a bike, you're going to experience a lot of wind that's going to be pushing you back, right? Because you've increased your speed, you're going to have a greater air resistance. So as it falls down, because it's accelerating because of its weight, the air resistance is going to increase. So the first point is that the air resistance, right? So the air resistance acting on the sphere. So we don't really need to say acting on the sphere, but I'm just going to put it there, right? So the air resistance acting on the sphere, guess what, guys? It actually increases. So the air resistance is going to be greater air resistance acting up on that thing. So what does that imply? It implies our second point. Our second point is that because of that, right, because of a greater air resistance, okay, the resultant force, right, the resultant force on the sphere, okay, the resultant force on the sphere, guess what, guys? It actually decreases. Why? Because the resultant force is actually going to be the weight, right? So the resultant force is going to be your weight, which is acting down, minus the air resistance, right? So if air resistance increases, that resultant force is going to increase until it actually becomes 0. That's very, very concerning, right? So the third thing is that the magnitude of the acceleration, okay, the magnitude of acceleration actually decreases then. So we're stating what happens to the magnitude of acceleration. The magnitude of acceleration actually decreases. Okay, so the magnitude of acceleration decreases as the resultant force actually decreases. As the resultant force actually decreases. So that's just a basic overline. Air resistance increases, resultant force decreases, acceleration overall gets to decrease. Very important. Okay. The sphere has a mass of 4 kgs. Well, this is a very, very big sphere. This is very irresponsible. This could kill somebody. Like it's like a sphere with 4 kgs. Okay. So we've been asked to calculate the total resistive force that is acting on the sphere at the instant when its acceleration is 1.9. So the acceleration is going to decrease. It's going to reach a point where the acceleration is going to be 1.9. Guys, ask yourself, what do you know? We have a sphere and weight is going to act down. Okay. That's basically what we know. Okay, but as weight acts down, we know also that the air resistance is going to act up. Okay, and then these two things are going to give you the resultant force, which is going to give you an acceleration. So let's just say our weight is W for convenience's sake. So our weight is going to be W. Then in this case, our air resistance is just going to be, I don't know, R. Let's just say R. Okay. So our resultant force in this case, Fc, which is our resultant force, is going to be equal to your weight acting down minus the value of R, right? The resistive force. So it means that W minus R is going to be equivalent to, your mass times your acceleration. So the value of R is going to be equivalent to W minus your mass times your acceleration, right? But your weight is actually going to be equivalent to mg. So R is going to be equivalent to, okay, mg minus m times a. Very important, guys. So your mass is actually 4.0 in this case times 9.81. Okay, you subtract 4.0 times your acceleration 1.9. That's going to give you an answer of 32 newtons. So we're going to put an answer of 32 and you get your 2 marks. What are the 2 marks, guys? The 2 marks is, can you calculate the resistive force, right? You get an A1 mark. So for you to get the answer and all that stuff. Then you get a C1 mark for the logic behind, finding the force, F is equals to mind, all that particular logic. Very important. The next question. We've been given a vertical rod that is fixed, okay, that is fixed to the horizontal surface of a table. Okay, a spring of mass 7.5 grams is allowed to slide along the full length of the rod. So this is our spring, right, with a mass. Okay, so the spring has a mass of 7.5 grams. Wow, this is a very light spring, but like, yeah, that's very important. So the spring is first pushed against the surface of the table. So you're going to compress your spring, then it's going to have an initial compression, then you're going to release it, and then it bounces and moves up the rod, right? So first, understand the question. What is the question even talking about before you even solve the actual question? Okay, so assume that the spring obeys Hooke's law, right? And that the initial elastic potential energy is equal to the kinetic energy as it leaves the surface of the table. By using the initial elastic potential energy, calculate a spring constant. What do we know, guys? We know that basically, know that the elastic potential energy is going to be 1/2 kx squared. Where does this come from? It's an expression that comes from the elastic potential energy from F is equal to K, from EP is equal to Fx, area under the force extension graph, and then you can say F is equal to Kx, but then you find it as an area and do all that stuff. But basically, what you need to know is that your EP, elastic potential energy, is going to be 1/2, okay, kx squared. It's a very important expression, guys, that you need to know, because the area is half Fx, the area of a triangle, which is going to be your shape, and then you're going to say half kx squared, right? So once you have this expression, you know that, but we know that the EP is going to be equivalent to EK. The elastic potential energy is going to be equivalent to you've guessed it, the kinetic energy. So in this case, 0.0048. Okay, so 2 zeros, 1 0. Okay, sorry. 48 is going to be equivalent to 1/2 K. What is our elastic energy? Converted, guys, to meters. Base units always in physics. So you have 2.1 times 10 to the power of -2 squared. So your value of K is going to be 0.048 multiplied by 2 divided by 2.1 times 10 to the power of -2 squared. So the value of K that you're going to get from this computation, we have 0.048 times 2 divided by 2.1 times 10 to the power of -2. All of that squared, and you're going to get an answer of 217, okay, 0.6870748, right? So we just express this 2SF because our answers, almost all of them have 2SF. Right? You're going to get an answer of like 220, right? Or 2.20 times 10 to the power of 3, or 2, right? I've heard that's a little bit much more effective. Whatever works for you guys, but 220 actually makes a lot more sense. We've been asked to calculate the speed of the spring as it leaves the surface of the table. What do we know? We know that EK is going to be equivalent to 1/2 mv squared, right? EK is going to be half mv squared, but EK, do we have EK? We do, guys. It's going to be 0.0048. Sorry, we don't have 2 0. Why do I keep on putting 2 zeros? Okay, we only have 1 0, right? So it's 0.048. It's going to be equivalent to 1/2, right? I don't know why I keep on putting 2 zeros. Okay, so I want to find the speed of the spring. The spring is going to have a mass of 7.5. So it's going to be 7.5 divided by 1000 times your velocity squared, okay? So 2 times 0.048 divided by 7.5 times 10 to the power of -3, right? The square root of all of that is going to be your value of V. Therefore, the value of V that you're therefore going to get from that particular expression itself, okay? So your value of V is therefore going to be equivalent to 3.6. So we're going to have a value of 3.6. Move on to the next question. The spring rises to a maximum height. So the spring is going to go up and up and up and up. So it's going to start here, right? At that point, then the spring is going to go here. Then it's going to go here. Then it's going to go here. So it's going to rise and up. Then it's going to reach a maximum height. Then it's going to gain gravitational potential energy, right? And you want to calculate for the movement of the spring, the increase in height of the spring after leaving the surface of the table. How far can it go? You compress it down, it's going to bounce. So how far is that going to go? Okay, we can calculate this. We know that EP is going to be equivalent to mgh, right? So delta EP is going to be equivalent to mg delta h. Okay, so delta h is going to be equivalent to delta EP divided by g times your mass. Okay, so your delta h is going to be, what is your delta EP, guys? 0.039 divided by 9.81 times 7.5 times 10 to the power of -3. So if you punch this on our calculator, 0.039 divided by 9.81 times 7.5 times 10 to the power of negative 3, you're going to get 0.53 meters. So it's going to go almost half a meter, right? It's going to go up that distance, right? Then we also calculate the average frictional force exerted by the rod on the spring. So guys, ask yourself, I have a gravitational potential energy, okay? But I have a certain kinetic energy at the beginning. But not all of that kinetic energy is going to actually be converted to gravitational potential energy. So what's going to happen? So work done against friction, right? So this is a very important statement that I need you guys to write, right? This is a golden statement, right? It's going to apply in a lot of scenarios, so you need to know it by head, unfortunately. So the work done against frictional forces is going to be equivalent to the loss in EK, right? The loss in EK minus the gain in EP. Okay, so this is a very important rule that you guys have to know. Okay, so we have a certain gain in EP, right? A certain gain in the elastic potential energy, so that gain in elastic potential, so we have a certain gain in elastic potential energy, right? So gain in EP. Then we also have a loss in EK. And if those two are not equal, so it doesn't only apply to EK and EP. Whenever there are energy transformations and the one is not converted to the other, meaning that some work is lost, right? So it means that the work that will be lost in this case is going to be equivalent to 0.048 subtract 0.039. Okay, so that's going to be the difference that you are going to get. But you already have the distance that have been moved. That is the increase in the height. You know that the work done is going to be equivalent to the force times the distance, right? So the work done divided by distance is going to be equivalent to your force. Therefore, your force is going to be equivalent to 0.00. Why do I keep on putting two zeros? 0.048 subtract 0.039 divided by 0.53, right? And that's going to give you 0.02 newtons, right? So it's going to be 0.02 newtons. Okay, move on to the next question. The rod is now replaced by another rod. Okay, this is a very now new rod, but that rod doesn't exert any frictional force, so it's a very smooth rod. So the initial compression X is now varied in order to measure the increase in height. Okay, so we now want to sketch a graph that shows the variation of X with delta H. Very, very important key distinction, guys. Okay, so now what do we know? Now there are no work done against friction. So it means that EP, which is going to be your elastic potential energy, right? So this is elastic, is going to be equivalent to EK, where EK is going to be your kinetic energy. That's also going to be equivalent to mgh. So that's your GPE. GPE. In this case, it's going to be gravitational, right? So it's going to be gravitational potential energy. So I'm just going to say gravitational potential energy. So those things are going to be equal. So I can use any equation that I want, that is delta H and that is X. So meaning I can use GPE is equivalent to mgh. So GPE is going to be equivalent to, okay, EK, right? So it's going to be equivalent to EK. So we're going to have mgh, right? No, not EK. Let's use EP, right? EP makes sense because we have compression, right? It's going to be equivalent to half kx squared. Okay, so your EP is going to be equivalent to half kx squared. So your delta H is going to be equivalent to, in this particular expression, delta H is going to be equivalent to half K, right? Divided by mass times G, all of that times X squared. But this whole expression, guys, is constant. Why? K is constant, M is constant, G is constant. So you're going to have a relationship where delta H is going to be directly proportional to X squared. But guys, this is a graph of y is equal to x squared. If you've done math, you know that y is equal to x squared, right? Or it's taught, I think. We have a graph like this. We also have a graph of y is equal to the square root of x. It's going to be a graph like this. You can punch it on a calculator that can plot graphs and you see these relationships. So in this case, we're going to draw a graph like so. So we're just going to draw a curve like this, like that, just to show the graph of y is equal to x squared. And the marking points, guys, one mark is for a curved line. So the M1 is for you just showing a curved line. Then you get an A1 for showing an increasing gradient. Those are the only marks that you're going to get, guys. So just try to be a little bit careful whenever you're answering these kinds of questions. Be very careful. Okay, move on to the next question. A ball Y moves along a horizontal frictionless surface, okay, and collides with a ball Z. As illustrated in views from above, that is Fig 4.1 and Fig 4.2. So you're playing snooker. If you haven't played snooker, well, there's snooker on the screen. So two people, or many people actually, hit a ball, and that ball hits another ball, and that ball hits some balls, and they get into holes. That's like an oversimplification of this game. But basically the point is, if you hit one ball, right, it's going to travel in a certain direction. So, but you can hit balls, then they travel in two opposite directions. So if one ball hits the other, then they travel in two opposite directions. With the situation happening here, we have Y, we have Z, they hit, they split. Okay, so then we can find the component of the final momentum in a direction perpendicular to PQ. So we want to find the direction perpendicular to PQ, which is the direction in this particular direction, right? So momentum is a vector. Why is momentum a vector? Because momentum includes, okay, momentum in this computation includes velocity. Since velocity is a vector, momentum is therefore also going to be a vector, right? Because of that correlation that, since one thing is a vector, the other one is also going to be a vector. So if we resolve this velocity into that component, we're going to have a velocity of 3.7 sine of 27. 3.7 sine of 27. So it means that your momentum, your final momentum, we know that momentum, okay, let's just move a little bit faster. We know that momentum is going to be equivalent to your mass times the velocity v. Your mass in this case is going to be 0.25. Okay, so it's 0.25 multiplied by 3.7 times sine of 27 degrees. Then you're going to get 0.42 Newton second. So you're going to have 0.42 Newton second. And then the second one is by considering the components of the final momentum in each direction, calculate mz. So the principle of conservation of momentum, guys, it states that if two objects move in opposite directions, or if we have two situations before and after collision, the momentum before will be equal to the momentum after, meaning momentum is conserved in any direction whatsoever that you actually have. So in this case, if we have a direction going up, we should have a direction that will be going down. Great, guys. We've established two directions, a direction going up, a direction going down, and we've assumed that those two directions are going to be equal. Okay, so what do we do, guys? Then we can equate those two ones. So we have mz 5.5 sine 44 in this particular case. So we have mz, okay, times 5.5 times sine 44. That's going to be equal to this 0.42 that we've just calculated, guys, in that above equation. Physics questions are related. Use your answers to find how they're related, guys. So mz is going to be equal to 0.42 divided by 5.5 times sine of 44. So your mz is actually going to be equivalent to 0.44 divided by 5.5 times sine of 44. So we're going to therefore get a mass of 0.11 kgs. So we're going to get a mass of 0.11 kgs. So very, 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 very important, guys, for you to pay attention to this. So during collision, let's go back to our snooker balls, guys. We have ball Y and ball Z. Ball Z hits ball Y. So ball Y and ball Z, have some little fight and then they hit each other. Okay. So ball Y is going to push ball Z, and ball Z is going to push ball Y. So they're going to push each other with two forces. So those forces are going to be equal in direction, and they're going to be opposite. Sorry, they're going to be opposite in direction and equal in magnitude. So they're going to be opposite in direction and equal in magnitude. I love this law. It's like Newton's third law. It's because, have you ever wondered, why is it when you hit a wall, right? Take your fist right now and punch it hard into the wall, right? So punch hard into the wall. What you're going to realize is you're going to be hurt. You're going to feel pain. But where's that pain coming from? Think about it. As you punch the wall, you apply a force on the wall. The wall is going to push the exact same force on you. So you're hitting the wall hits you. So you feel the pain. The wall also feel the pain. Poor wall, right? But the wall won't move. It won't be damaged. But you will feel the pain. But the wall has also felt the same pain too, right? So, it's just a fun way of thinking about Newton's third law. Okay, so we've been given two blocks, block A and block B. We're done with snooker. We're now moving on to blocks. Okay, so they move directly towards each other. Then they collide perfectly elastically. Perfectly elastically. Oh, that's funny. Okay, so perfectly means that no energy is lost from that system. Momentum is conserved. Energy is conserved. But we have a rule, guys. So you have block A moving with 4 and that one with 6. Then after they move in opposite direction, which is 2. That is block A. Also, we want to find block A. Okay, so block A moves a certain velocity that we don't know. We're just going to say that velocity is V. But the other one here is going to move with the same velocity that we do know, which is going to be 2 meters per second. Okay, guys, I want you to learn something here. Whenever you see a momentum question that is velocities before and after, you're going to need this golden rule. If you have a notebook, now is the time to write something down. If you don't, go get it. What are you waiting for? This is the golden rule that's going to help you with any question that you're going to answer that involves relative speed of separation and relative speed of approach. Here's how it works. Imagine you have two cars, car A and car B. Now those cars are going to move towards each other. Okay, let's say they're moving far away from each other. Right, you add their relative speeds of separation, right? Because if two things are moving away from each other, car A moves with 4 meters per second and car B moves with 8 meters per second, meaning that the relative speed of the separation is actually going to be 8 plus 4, 12. Because for car B, relative to car A is going to move at 12. Because car B is moving so fast at 8 and car A is moving away at 4. So it's going to be to car B as if it's moving away at 12 relative to car A. But for car A, it's going to be looking as if it's 12. It's moving at 4, but B is moving very, very fast away. So it's going to be also 12. So relative to each other is going to be 12. But if two cars move in the same direction, one after the other, they're not going to see that. We're going to subtract the relative speed of separation because it's going to be as if one is approaching the other. So the relative speed of separation is actually going to subtract. So here's the general rule of thumb. Write this down, guys. This is why you're writing down. Whenever objects move in opposite direction, right? Directions. To find the relative velocity, right? So to find the relative velocity, you add, this is the golden rule, guys. Let's put it in gold. You add, right, the relative velocities, right? So you just add the velocities, okay? And then when they move in the same direction, so this is the first rule, then this is the second rule. Then when they move in the same direction, okay, if they move in the same direction, what are you going to do, guys? You're therefore going to subtract, okay? You're going to subtract their velocities. Okay, so whenever you see opposite directions in momentum questions, before be it separation, be it approach, opposite, you're going to add. Same, you're going to subtract. How I memorize this? Well, same starts with an S. Okay, so same starts with an S, meaning that S subtract. Opposite has two P's. To me, they look like D's that are flipped down. So it's going to be add. Right, so I've always added in my mind, opposite, add, same, S, subtract. Okay, so in this case, ask yourself, before collision, relative speed of approach, are they moving in opposite direction? Yes, this one is moving to the right. This one is moving to the left. So add them. 4 plus 6 is equal to. After, this one moves that with V. V plus 2 equals 2. Therefore, V is going to be equivalent to 8. That's how you think about these questions overally. I'll move on to question 5. This is a polarization question. Okay. Now, because of time, I'm not going to go through all the polarization questions, but if you have any queries or challenges regarding this topic, I highly recommend that you watch my video on my channel. I did a whole video on polarization. I first explained it with clear and easy to understand animations, how the polarization topic works, and I also solved worksheets for different past papers. I had like 2 separate videos for different past papers. You can also check that out. They should help you understand polarization a little bit better. So that when you come to questions like these, you already have a bit of an understanding. But basically what I want you to understand, when we want to sketch a graph. Okay, so when given a beam of vertically polarized light, we're going to have light that's going to be traveling in this direction, like this. Okay, so I'm just going to explain it a little bit. Okay, So the transmission axis is initially vertical. Initially vertical means that all the light can pass through. So you're going to have a maximum value of intensity. Intensity meaning how much light do you read on the other side? It's going to be very, very big, right? So since your intensity is going to be big, right? Since you're going to have a very, very big intensity value, what then you're going to do is then you have to consider, right? This is very important for you to consider, guys. You're then going to have to consider in this particular scenario, if you look at it, at 90 degrees, it's going to be like this, right? At 90 degrees, nothing will enter through, guys. So it's going to be falling down at this particular point. At 180 degrees, it's going to be like this, right? Relative to where you started. Malus law is always measured relative to where you start. So it's going to be like this, right? So it's going to be at 180 degrees, something like this, right? Again, it's going to be a very high maximum value. Okay, and then if you go to 270, it's going to be low. 360 is going to be back up again. It's going to be a high value. Then you just draw a sinusoidal graph. So you just draw something like this, right? You have something like this, something like that, something like this, and something like that, right? So basically, that is what they expected you to draw. Again, you were asked you need light intensity with maximum values. Then you're going to need a sinusoidal shaped curve. Very important. For the second question, we're given the intensity of the incident beam. Then we're given the intensity after polarization has occurred. What are we going to do, guys? We're going to use Malus's law. Again, guys, if you're unclear on polarization, like I don't understand Malus's law, I have a video. Go and watch that video. It's going to help you understand more. But basically, Malus's law says that the intensity that you get out is equivalent to I naught cos squared the initial theta. Cos squared theta, guys, means that I is equivalent to I naught. Cos squared theta actually means that is cos theta squared. This is a very, very important distinction for you to make, right? So I over I naught, the square root of that is going to be equivalent to cos theta. Therefore, the angle theta is going to be arc cos the angle of the square root of the initial one, which is going to be, in this case, I, the one you transmit, 4.2. The initial one is going to be 7.6. You're going to get a value of theta that's essentially going to give you about 42 for 1.9788357.9. You're going to get about 42 degrees, guys. Very important. Okay, move on to the next question. We've been asked to state what is meant by diffraction of a wave. What is meant by diffraction? This is again a recall question. Okay, a recall question. So what's the definition, guys? The trick to physics, have your own separate notebook, guys, where you write using objectives and you write every single thing. These are important questions. If you have a question that answers the objective of diffraction, you're going to need these notes. And get your answers from the marking scheme. Guys, you might have a test book, but if that test book does not contain answers in the marking scheme, unfortunately, you won't be marked. So whenever you have definitions, try to use marking scheme definitions. That will help you, know what exactly is examined upon. So the actual definition is when a wave, this is the spreading of a wave, okay? So diffraction of a wave, this is the spreading of a wave, okay? So a wave spreads, as you can see on the screen, the spreading of a wave, as you can see over there, into a geometrical shadow. We don't really need this, but like it's the shadow that will actually exist over there, right? Into the geometrical shadow, when it passes through an aperture. So through an aperture is like a small hole, right? That's like an aperture, okay? Through an aperture or around an edge. Around an edge, diffraction can still occur, guys. Diffraction doesn't stop occurring because we have arrived at an edge. So basically, that's the definition of diffraction. For question C, we're given a beam of light with that wavelength that is incident normally on a diffraction grating, and we've been asked to calculate the line spacing d of the diffraction grating. Whenever you see the word grating, one equation comes to your mind. N lambda is equivalent to d sine theta. So your value of d is just going to be n lambda divided by sine theta. Ask yourself, what is n? Your n in this case is 3 because that's the order. What is your wavelength? Your wavelength is 4.3 times 10 to the power of negative 7. What is your angle? Your angle is sine. Your angle is measured relative from this line, guys. Relative from this line, your angle is actually 68. So it's going to be sine of 68. then that's going to give you a value of D of just 1.4, right? That's a rounded off value. So you're going to get 1.4 times 10 to the power of negative 6 meters. 1.4 times 10 to the power of negative 6 meters. Okay. Then we also determine a different wavelength of visible light that will also produce a diffraction maximum at an angle of 68 degrees. Okay. So we know that visible light lies between 300 to 700 nanometers. Okay. So we want to find at what, we don't know what order. Imagine if light is a very high wavelength, it's going to diffract more. Okay. It means that at a very low order, you're going to have it having a very high angle of like 68 because it's going to have a very high wavelength. So at a very low order, it's going to have a greater diffraction. So we can test that and see what value of lambda do we get at different values, and we can then calculate the value of n that we have. So we know that d sine theta is going to be equivalent to n lambda. So we want to find the value of lambda and see if it lies between that range. So lambda is going to be equivalent to d sine theta divided by n. So we can try for n is equals to 1 and try for n is equals to 2 and n is equals to 3. But n is equals to 3 we don't, because we already have used 3 in that particular equation. So we start with 1 and 2. So lambda 1 is going to be equivalent to 1.4 times 10 to the power of negative 6. So 1.4 times 10 to the power of negative 6, okay, times sine of 68 divided by 1. Okay, so it's basically times sine of 68. We don't really need the divided by 1. Then you're going to get 1.29, okay, times 10 to the power of negative 6. That is not possible for visible light, because visible light lies in, 3 times 10 to the power of negative 7 and 7 times 10 to the power of negative 7. Then if you try for 2, so we're going to have lambda 2 being equivalent to 1.4 times 10 to the power of negative 6 times sine of 68 divided by 2. Then this is going to give you a second value of lambda. Very important. So if you divide this by 2, it's going to give you 6.49 times 10 to the power of negative 7, which is going to be 6.5 times 10 to the power of negative 7. Guess what, guys? We do find that in the visible, light spectrum. So again, questions that you need to think. What value of n do I need and what lambda do I get? Just think about it in that way. Okay, electricity. We're almost done. 2 more questions and we call it a day. Okay, so for electricity, you need to know basic things. Again, guys, how are you going to study physics? You're going to have a syllabus, you're going to have past papers, and you're going to use your syllabus to write your notes, and you're going to use the test book. Again, you have other channels that you can use that are going to really help you. Again, on my channel, I'm still developing some worksheets that you can use, but again, try to have a lot of variety of notes and be able to gain a little bit much more from studying physics. Physics is very interesting, but you have to have a very positive attitude. Because you're going to learn it either way. The mere fact that you're actually doing physics means you have to like it one way or the other, right? That will actually help you than do harm. So we know that R is going to be equivalent to rho L divided by A. So R times A divided by L is going to be equivalent to rho. Rho is going to be the resistance per unit length times the area A. So the resistance per unit length is 0.92 times the cross-sectional area, 5.3 times 10 to the power of negative 7. That's going to give you guys 4.9 times 10 to the power of negative 7. So 4.9 times 10 to the power of negative 7. Okay, we're given a battery of EMF E and negligible internal resistance. Very, very good. It doesn't waste all our power. That is connected to a fixed resistor. So the fixed resistor is 1,400. Okay, and then we have a light dependent resistor, which is over there. Then we also show that the current, in the LDR is 4.0 times 10 to the power of negative 3. Guys, if I'm being honest with you, I don't like the way that voltmeter is connected. So what am I going to do? I'm just going to erase it. Again, this is my question paper. I'm in an exam. I can do anything. Okay, and then connect it in a way that just, looks good for me. Right, something like this. This is still true. Right, because I still have the same connection points. Here and here is the same as here and here. So I can do anything that I want. I can remove anything that I want, really, basically. Because of physics, right? Physics allows you to do some crazy things. Okay. Current, we know that V is going to be equivalent to IR. So therefore I is going to be equivalent to V divided by R. Okay, so V divided by R is actually going to be equivalent to your value of I. Okay, So I is going to be equivalent to the voltage that you're going to get, which is 6.4, divided by the value of R, which is for the LDR, is going to be 1,600. 1,600, and then you're going to get an answer of 4.0 times 10 to the power of negative 3. Okay. Then calculate the number of free electrons passing through the LDR in a time of 3.2 minutes. What do I know? I know that charge is equivalent to IT. My current is 4.0 times 10 to the power of negative 3. My time is 3.2 in seconds times 60 is going to be 0.768. So that's my first mark. I have obtained it. The next mark comes from you knowing that, the number of electrons, right? The number of electrons is going to be equivalent to the charge that you have divided by the charge of one electron. So one electron has its own charge. So the charge that you have as a whole divided by the charge of one electron. So 0.768 divided by 1.6 times 10 to the power of negative 19. That's going to give you about 4.8 times 10 to the power of 18. So we're going to have 4.8 times 10 to the power of 18 electrons. So remember, if you have a particular charge, the number of electrons will be equivalent to your charge divided by how many electrons, how much charge each electron actually has. Okay. Then we've been asked to calculate the EMF E. The EMF E, what do we know, guys? We know that E is the total EMF. So E is going to be equivalent to I, right? Voltage is going to be I times the resistance of the LDR plus I times the resistance of the fixed resistor. So I can factor out I, and then I'll be left with R2, so RL, right? Plus then RF, which is going to be that particular value, right? So something like this. So basically my I is going to be 4.0 times 10 to the power of negative 3 times, then if I'm going to add those guys up, 1,600. Why do I keep on putting extra zeros? Okay, 1,600 plus 1,400. And then we're going to get 12 volts. So this is going to be 12 volts. Okay. Determine the ratio power dissipated over power dissipated. I love these questions, guys. Whenever you hear the word ratio, ask yourself, what equation do you know? Right? You know that power is equal to I squared R. Okay. Power is equal to I squared R. So basically you're going to have here I squared R divided by I squared R of L here, then of F here. Your I is going to be the same. So basically it's going to be your resistance of L over your resistance of F, which is just going to be 1,600 all over 1,400. I'm going to give you a ratio of 1.1. So we're going to have a ratio of 1.1. Okay. For C, the environmental conditions that cause a change in the decrease of resistance happen, but the temperature remains constant. So we've been asked to state if there's an increase, a decrease, or no change to the internal resistance of the LDR. Okay, let's think about this. We know that for an LDR, you have probably seen this graph before. That's what I assume. Okay. If you haven't, well, congratulations, you've seen a new graph, right? You have the resistance here, then you have the light intensity here. So for your syllabus, light intensity. So for your syllabus, the assumption is whenever the light intensity increases, right? So whenever the light intensity increases, the resistance actually decreases. Wow, that's pretty shocking. As the light intensity increases, the resistance actually decreases. So if the resistance, it never gets to zero though. So if the resistance decreases, what does it mean about the intensity? It actually increases. Then for this one, we know that the current is going to be equivalent to IR. So V is equal to IR rather. V is going to be equivalent to IR. So it means that I is inversely proportional to 1 over R. So it means that if the resistance decreases, the current what? The current will actually increase. Okay. If the resistance of the LDR decreases, electrons are very smart. What they do is they know that if you have the greatest resistance, we're going to give you the greatest amount of current. So since the first resistor has a very great resistance, it's going to get a large amount of the current. So the reading on the voltmeter is going to be more for the fixed resistor. But the LDR is going to have a decrease in the resistance, meaning that it's also going to have a decrease in the voltage. So the reading of the voltmeter is therefore going to decrease. Right? Something like that. Okay. 7a. We are done. This is the last question on particle physics. Then we'll be asked to underline all particles that are not fundamental. So it's going to be baryon It's going to be a nucleon, right? A positron, that's a fundamental particle. An antineutrino, again, that's another fundamental particle. Okay, move on to question B. A nucleus of thorium 230 and 90 actually decays by emitting alpha and beta particles to form lead 206. That's thorium and that is lead. Okay, so we want to determine the number of alpha particles and beta particles that have been emitted. Okay, so we have 230. Okay, then we have 90 at the bottom. Okay, and then we're going to have TH. Then that's going to give us 206. Then we're going to have 82 and PB. So what I'm going to do is I'm just going to subtract 230 and 206 and see how many have I actually lost. How many alpha particles have I actually lost? So 230 minus 206. So 230. Sorry, there's a minus in here. 230 minus 206. So basically, that's going to give me 24. But I know that one alpha particle weighs a 4. So 24 divided by 4 is going to give me 6. So meaning that I have 6 alpha particles. Okay. So if I have 6 alpha particles, so it's going to be plus, right? Those 6 alpha particles are going to be lost. This is going to be our resulting nucleus, but we're still going to having a 90. So if we're going to do it in a sequence, we're going to have 230, then we're going to have 90 TH, giving us 206 of PB plus 4. So it's 4 times 6, that's going to be 24, right? And then we're going to have 2 times 2 because there's a 2 at the bottom. That's going to be 2 times 6, that's going to be 12. Okay. So if you have 90, you're going to lose 12. Okay. Then you have 80 here, right? But, right, so sorry, you have 82. Okay, so you have 82 here. Okay, so 82 plus 9 plus 12 is going to be equivalent to 94. So how many alpha particles do you need? You need 4 alpha particles for the denominator to actually add up. So sorry, 4 beta particles in order for the denominator to add up to 90. So you're gonna have 4 beta particles, then you're gonna have 6 alpha particles. Okay, so it's going to be 6 and then it's going to be 4. If it's unclear, guys, please put it in the comment section. This is for free. Just like comment, I didn't understand A, B, C, D, and I'll happily respond that. Okay, so a meson has a charge of -1, where E is the elementary charge. The composition of the meson includes a charm antiquark. State and explain the possible flavor or type of the other quark in the meson. So we know that it's charge in quark 1, okay, plus the charge in quark 2 is going to be equivalent to -1e. For quark 1 is going to be your charm quark. But how do you know if charm is going to be positive or negative? Well, we know that anti-quark reverses. If it's positive, anti-quark is the opposite charge but the same mass. But I want to figure out, well, how exactly do I find this particular question? Well, what I know is I use this particular way of memorization. So I have charm and I have strange. These were always very hard for me to memorize them, but I figured something out. Strange has an N. Look at this, guys. Strange has an N. So that N stands for a negative, right? Then you'll be done. Once you figure out that that's a negative, you just know now it's -1/3. So for me, it was always hard. Is it positive 2/3 or -1/3? I knew that if it's a negative, it's going to get the smallest number between 2/3 and 1/3, but I didn't know what. So then I said, okay, if I put a negative from strange has an N, -1/3, charm, we have positive 2/3. So it means that a charm antiquark is going to have -2/3, right? Plus the charge on quark 2 is going to be -1e. So quark 2 is going to have a charge of -1e plus 2/3e. So we're therefore going to have -1/3e. And this can be a lot of particles, guys. This can be a lot of particles. Number 1, this can be a down quark. You get a mark. You can say it's a strange quark. You get a mark. Whoever says it's a bottom mark, you get a mark. And everyone gets a mark, right? And we are done. So that's a physics paper 2 paper for you. So if you're in the process of preparing for an examination or just trying to help practice physics, do a lot of past papers and be a little bit organized about how you answer those questions. That will help you, be able to answer and practice more often. Thank you guys for watching. If you like this video, please do subscribe, like and comment, and I'll see you in the next one.